Okay, good afternoon. So let us continue the lesson. So something was actually left from the previous session. I would think that it would be better if I go through this part a little bit deeper to review things. So the first thing that we talked about was the definition of integrability. Okay, so let me write this definition. This is actually a recall or a recap for the time being. I am deviating a little bit from the notes, and then I will come back to the notes, okay? So let f be a function that is bounded on the interval. So let me make it shorter. When I write this, you know that this means interval, closed interval, a and b. Okay? If there exists a unique number I such that L, F, and P less than or equal to I less than or equal to U, F of P. You remember this is the notation that I use for the lower sum, and this is the notation that I use for the upper sum. So I'm saying that if there exists a unique number I such that this happens, but for every partition P of this interval A and B, then F is said to be integrable on A and B, and the number I is called the integral of F on A and on this interval A and B, and is denoted by this symbol that you already know. Okay? So that is the definition that we have for integrability. So if a function has this property, if a function is a bounded function on a closed interval, if you can somehow find a unique number which is less than or equal to all upper sums and at the same time greater than or equal to all corresponding lower sums, if that number is unique and exists, that number is called the integral of your function on that interval. Yes? And in that case, you say that my function is integrable. So you see that there is no notion of derivative involved in this definition at all. Yes? I'm just defining it in this way, and this is actually a subtle definition. It's much harder than the definition that you had for the derivatives, yes? Because in that case, I gave you a function, I gave you just one single number, and I could ask you, is the function differentiable at that number? Rather than saying that is my function is integrable over an interval, yes? In that case, what you did, you just calculated the limit. So that was a limit process. You knew how to calculate a particular limit. If there is an answer to that limit, you say that yes, the function is differentiable and the value for that limit is the derivative. But this is a very strange way of definition, apparently, yes? So because even understanding, having control in your brain about the lower sums and upper sums are not that easy, because I told you that partitions are the numbers that you choose in the interval from A to B. They can be completely irregular, so there is no regularity for them that you choose. So I mean that this is, I want you to understand that is actually a subtle definition, okay? At least it is not a practical definition. From practical point of view, if you want to find that number I, you have a big problem in front of you, okay? So that's not that easy, even for the simplest possible functions that you can imagine. Okay, so this is what we have, and then one of your friends actually asked a question that, can we have a function that does not have this property? So I gave you this example. It's good, it's actually a classic example in this case. So that is the Dirichlet function, yes? Okay, a function like this, let me call it D this time, it's better for Dirichlet, yes? So d of x is defined in this way. It is defined to be 0, if it is defined to be 1, if x is a rational number. A rational number is a number like 1 over 2, 3 over 5. Fraction numbers that numerator and the denominators are coming from integers. And then it is 0, it is defined to be 0 if x is not rational, does not belong to the rational numbers. For example, the square root of 2. So in principle, if I ask you what is the value of the Dirichlet function at minus 1 over 2, you say that, okay, because minus 1 over 2 is a rational number, the answer is 1. If I ask you what is d at 0, you say that 0 is a rational number, so d of 0 is 1. But if I ask you what is d of the square root of 2, or for example, what is d of the square root of 2 plus the square root of 3, or what is d of pi, because all these numbers are irrational numbers, the value for this is just 0. So that's the way that we define the Dirichlet function, yes? So, and then, for example, for definiteness of discussion, let me just take a very simple interval from 0 to 1, okay? Last time we showed that this Dirichlet function is not integrable on this interval, yes? Because, for example, if you want to do this, if I want to remind you, just help me to do that. So what is L of f and p? So I would consider that p is an arbitrary partition for this interval 0 to 1. Then you remember the definition of that one. This is sigma I, and then you choose minimum number for the function in the interval, the minimum value, not minimum number, sorry. And then you multiply it by the length of that interval, which we denoted by this symbol. But you remember that because in any subinterval, definitely we have rational numbers and irrational numbers simultaneously. So the minimum value for the Dirichlet function on any subinterval will be 0. Because the Dirichlet value is either 0 or 1. And of course, if you have an interval, in that interval, definitely you have irrational numbers, and then the value of that Dirichlet function at that particular point is 0, and that is your minimum. So this means that all of them are 0, and then even you don't care what this number is. If you calculate this sum, the sum becomes 0. Yes? And then I calculated u of f and p for the same function. Again, I am assuming in my head that p is an arbitrary partition of that interval, and I want to calculate this. So if you recall the definition is very similar, but instead of taking the minimum value, this time you take the maximum value, delta xi. Yes? So what happens here, the maximum value for the Dirichlet function, I have to write Dirichlet function here. The name of my function is d. So mi, what is mi? The maximum value of the Dirichlet function is 1, and it doesn't matter on which interval you're looking at the function. Definitely you will get a rational number, so its maximum value is 1. So mi is 1 times delta xi. So this becomes the sigma delta xi. But do you remember what that number is? Delta xi means the length of the ith interval. What I am doing, I am adding the lengths of all subintervals. So it becomes the total length of my interval. But the total length is 1. So this answer becomes 1. So by the way, this is a very simple classic example. You see that I was able to calculate the lower sum and the upper sum very simply. It's not usually the case, okay? And I don't need to bother about what are the points that I am choosing in between. It doesn't matter at all. The lower sum is 0, the upper sum is 1. Okay, now let us answer, because there are two words that you need to be careful. There exists, existence, and uniqueness. For the existent part, we don't have any problems, yes? Because we realize that the lower sum is always 0, the upper sum is always 1. So I do not have any problems with existence, yes, because I have how many numbers I have between 0 and 1 that can play the role of this I, infinitely many, any number that you choose. And that's exactly the problem. I want to have a unique value, not infinitely many values, yes? So this means because of that, I was able to find, but unfortunately or fortunately, I found infinitely many, which makes problem for me. So this is not integrable, yes? Is that clear? That is one classic example that you see a function which is not integrable. And that is also, I told you that if you want to imagine this function, it's hard to imagine, but for example, you have this line from 0 to 1. If you have a rational number, this point is hollow, and then you jump to height 1. But the next point, I don't know what is the next point. Even if I say the next one, there are infinitely many points which are rational and irrational suddenly between that small interval. So I mean that when I reach to a rational number, I jump to 1. When I am irrational, I remain 0. But this jumping up and down is so much that there is no way to give an idea about the area below the curve. Yes? So that is reasonable that this function is not integrable. Okay, but then I gave you another example, which we didn't finish, and try to finish it today. So I gave you another very simple function, by the way, f of x equals to x, and then I gave you the interval from 0 to 1. I want to check the integrability of this function on that interval, and in the case if it is integrable, I am asking you to find its integral, yes? Okay, so do you remember I did some calculations? I write the results here. So I did this. I say that let P, starting from X node, which is the first number always, and X1, X2, up to Xn minus 1, up to Xn, which is the last one. So I would say that let this be a partition, yes? Be an arbitrary partition, not necessarily regular or something, just a bunch of numbers between 0 and 1. But when I say partition, you remember x1 is less than x2, x2 is less than x3, etc. I am arranging them ascending order. So let be a partition of 0 and 1. Okay? I don't want to repeat the calculations, but last time we calculated the lower sum of this function for that particular arbitrary partition, and I got this result. I got this is 1 over 2, I think minus 1 over 2 sigma I goes from 1 to n xi minus 1 squared. This is what I got by that calculation if you refer back to your notes. Unfortunately, the video was not recorded. And then u, f of p, I calculated that one. I get a similar expression, but with positive sign in between. Yes? This is what we got. But it is very simple to idea. So what are these xi's and xi minus 1s are these numbers. But this is clear that because of this power of 2, and because xi is always greater than xi minus 1, this is a positive number. By the way, it's always a positive number because xi by definition is always larger than x minus 1 of. We also have power of 2. So it's guaranteed that this combination that you see here, that appears here and there, is a positive number. Yes? So this means that this is less than or equal to 1/2 because this is 1/2 minus a positive number, and this is greater than or equal to 1/2 because that is 1/2 plus a positive number. Yes? So what I realized by this calculation is that the existence part, I achieved the goal, yes? Because I realized that, therefore, for all P, by this I mean for all partitions, I realized that the lower sum is less than or equal to 1/2, and it is less than or equal to the upper sum. Yes? So I was able to convince you that there is a number which is less than all upper sums and greater than all lower sums. But I cannot jump into the conclusion immediately that this is integrable. Because do you remember in the Dirichlet case, we also found a lot of numbers. So I have to guarantee that this number is the only number with that property. Yes? So I want to show that. So we need to show that 1/2 is the only number with this property. Yes? What by this property I mean it is smaller than all upper sums and greater than all corresponding lower sums. But to do this, I considered now a different partition, a class of partitions which I discussed about last time, the regular partitions. Okay, now let me this time, I would say that let me write Q sub n. Let me write it in this way: x naught prime, which is again 0, and x prime 1, x prime 2, up to x prime n minus 1, and x prime n to be equal to 1, be a regular partition of 0 and 1. Yes, this time I am looking at a different class of partitions. Here, everything I said is completely generic. For all partition, it is correct. But now I pay attention to a particular class of partitions, irregular partitions. Okay, but because these formulas that I achieved for this one and this one are completely generic, for any partition it works, so it also works for this particular partition. Yes, is that clear? Because that was for any partition without any constraints at all. This one is equal to that, and this one is equal to this. But this is also true for this particular partition, yes? Okay, but for this particular partition, let me calculate this sum and look at it, okay? So in this case, the sum of x prime, because instead of xi, I put x prime I minus 1, to power 2. Let me calculate this sum for you. In this case, it is possible to calculate. Okay, how can I calculate? Can you tell me? In this case, my partition is regular. It means that the lengths of all subintervals is the same number, or the same numbers. What can I write for that? I'm asking these questions because in your head, when you calculate them, you will actually follow me. So how should I do that? This is, if I ask you what is this number here, okay, say something for it. What is this number? xi minus xi minus 1 is the length of the ith interval, yes? And I told you that the regular partition has all the lengths to the same number. So what is the length of each one of them? So xi prime minus xi minus 1 prime is actually the length of the whole interval, which is 1 unit divided by n. Agree? And it doesn't matter for all I, not just for, so for all I. So this means that this sum in this case can be calculated easily because this goes from 1 to n. Instead of this one, I write 1 over n squared. This becomes sum 1 to n. This becomes 1 over n squared. Yes? So what I am doing, I am adding this constant term because you know that n is fixed. 1 over n squared is fixed. I am adding this number n number of times. So this becomes n times 1 over n squared. And this becomes 1 over n. Yes? Yeah. So then if I go back here, then what can I say? I can say that the lower sum for f that corresponds to this partition is equal to 1 over 2 minus 1 over 2 times this, which I calculated for you. It's 1 over n. So it's become 1 over 2n. Yes? So it becomes 1 over 2 minus 1 over 2n. And if I ask you the same question for u, this becomes 1 over 2 plus 1 over 2n. Yes? So because this is the same thing, yes? This part is 1 over n. I multiplied by 1 over 2 and wrote these formulas for the new partition. Okay, but now I hope that you agree with me. So again, 1 over 2 is between these two. So that is not surprise because I showed that 1 over 2 is between all upper sums and lower sums. So that's not surprise. The important thing is that let us consider what is happening here. So this 1 over 2 is here. Okay? My claim is that you cannot find any other number except 1 over 2 with the property that it lies between all upper sums and lower sums. So my claim is that you cannot find such a number with that property except 1 over 2. So this means that 1 over 2 is unique. How can I show that? I want to give you an idea how to prove it, but this can be made mathematically rigorous. So my claim is that 1 over 2 is the only number with that property. If you say no, so it means that you can find another number with that property. Yes? So let us say that you found this number. Let me call it A. Okay? I want to show that no, A cannot be the number with that property. Okay? Why is that? Now, momentarily forget about A in your head, and then let us concentrate here and there. This is 1 over 2 plus a positive value. So, for example, let us consider this is 1 over 2 plus 1 over 2n. Yes? And then this is 1 over 2 minus 1 over 2n. Yes? This is my situation now. If the number you have chosen is already outside this interval, okay, so this means that this does not have that property. Yes, because I want to, you are claiming that this number A is always between lower sums and upper sums, always, yes? If this is the case, so if this A is somewhere here or somewhere there, it's already a contradiction, yes? Because I found this lower sum and upper sum doesn't cover that point, yes? But you might say that, how do you know? Might be A is here and it is already included. But I would say that this is true for arbitrary n. I start increasing the value of n so that this number becomes so small that this, because you know that by increasing n, what is happening? This fraction becomes smaller, so this point is getting closer to 0.1 over 2. Yes? So what happens, if this is the case, I say that, okay, this n does not work for this A, but be patient. I will increase the value of n, then eventually this point will pass through this A. So it means that I will be able to make n bigger. For example, let us write this with a bigger n, with a sufficiently large n, with this property. Yes? Do you agree with me? So it means that if you say that there is a number with the same property, but not 1 over 2, I showed that you can find a lower sum and an upper sum which does not include that point by increasing the value of n. So this shows that, first of all, 1 over 2 has that property, and 1 over any other number does not have that property. So it means that 1 over 2 is the unique number with that property. Is that understandable? So let me repeat, might be that's, so you see, let me just once more repeat it. So here, my claim, so you know that here is 1 over 2, yes? And here, for any choice of n, so you see that this value is always less than 1/2, regardless of my choice for n. Because 1/2 minus a positive number is smaller than 1/2. Yes? And 1/2 plus 1 over 2n, regardless of my choice for n, is always larger than 1/2. And 1/2 is exactly the midpoint. Yes? One thing you can see that, what happens if I start increasing the value of n? When I increase the value of n, this 1 over 2 becomes smaller. So my distance to 1 over 2 becomes smaller. So it means that by increasing n, this point starts moving towards 1/2 to the left, but this one starts moving to the right and closer to 1/2. Is that clear? By increasing n, I am shrinking this interval. Okay? If you say that there is another number with that properties, which is not 1/2, okay? If it is already there, I don't have any problems because this is not included in my interval. But you might say that, how do you know? Might be this number is here. Okay, I would say that let me increase the value of n. Eventually, these points will actually pass through this point, and this point will be outside then. Okay, it doesn't matter if you say, okay, let us make it closer. If you make the number a even closer, I will increase the value of n even more. So eventually, I will exclude that point that you are claiming it might be another number with that property. Yes? Is that clear? Yes?
Doesn't this only prove for regular intervals?
No. That's my point. No. That's the point. In Adams, I think it's very strangely stated because, of course, next theorem, I want to say that it is only enough to look at the regular intervals. But by the definition, no, I am just trying. I made it a little bit more complicated because exactly of your question. Okay, so if you don't understand it, I can repeat it again. So what I showed, this part is for all partitions. Okay, so this proved that there is at least one number with that property. Now, for the uniqueness part, I am saying that I want to show that 1 over 2 is the only number which is smaller than every upper sum and greater than all lower sums. Okay? If you say no, it means that you have another candidate here, okay, which satisfies that condition. But now I say that no, you cannot satisfy that condition for this number because there are some lower sums and upper sums which violate that property. Okay, is that understandable, the logic? So this is not a special case. That is actually the general proof. Yes? Can you digest that? Yes? Yeah, that is actually the reason that I make it a little bit more complicated than that's written in the book, because exactly of this point. Yes? Okay. So you see that it has nothing to do with calculations. So, but of course, so it means that at the end of this part, I can be sure that the number that I found there is exactly my integral. So at that point, I say two things. I say that yes, this function on this interval is integrable, and the integral of that function on that interval is exactly that number 1 over 2. Yes? So this means that at this point, yes, f is integrable. and the integral from 0 to 1 f of x dx, which actually in this case from 0 to 1 x dx is 1/2. Now I think you appreciate Newton's method to calculate this, yes? Because Newton's method to calculate this is a little bit strange because it has nothing to do with derivatives here. So Newton's method is that find a function whose derivative is x, which is not actually apparent in this method at all. And then what is that function, which is a primitive function, x squared over 2, and then put 0 and 1 and subtract them. So that is your number, just a half of a line, yes? So this will actually do the calculation for all these things. Any questions? So anyway, I want to see that this is a subtle question. This function is integrable and its integral is 0, 1 using first principles. But we never do that in calculations, especially in calculus. We just use Newton's formula to calculate the integral. Okay? Okay. But for example, Newton's method is silent for Dirichlet function. Yes, it cannot say anything about that because when you want to use the Newton's formula, there is one other constraint on the function. Do you remember I talked about that? So what was the main property of the function so that for that function you can use Newton's formula? It should be continuous, yes? So it has nothing to say about the Dirichlet function, integrability of the Dirichlet function or whatever, okay? Anyway, now I want to say that, okay, life, thanks to mathematicians, is not so hard. So you can only look at, I want to skip the proofs, but I want you to see them. The theorem is this. Let me make sure that I haven't, okay, I want to write the theorem here for you. Okay, so there is a theorem that tells you that you don't need to work so hard. You can always work mainly with regular partitions rather than all sorts of partitions. So that is the theorem. Okay, so let's f be a function that is bounded on the interval from A to B. Okay, and let me write Pn, x node, which is A, x1, x2, up to xn minus 1, and finally xn, which is B. Be a regular partition of, I usually write the partition wrong. Yes, partition A and B. We have this. If the limit of lower sum f Pn, when I increase n indefinitely, becomes equal to the limit of u f Pn when n goes to infinity, then f is integrable on this, and the common value for this limit is the integral. Okay, and the common value of these limits is integral from A to B f of x dx. Okay? So this is much simpler because, again, it's a limiting process. It's not that easy as before for the case of derivative, but it's still much more reasonable than that one. So this means that if I give you a function which is bounded on a closed interval, what you do, you just write a generic partition, regular partition, okay? And then calculate the lower sum and upper sum for that partition. Because in this partition, n is a variable and you can choose n whatever you like, you get a sequence of numbers here and there. You calculate the limits of these sequences of numbers. If it turns out that the limit of these these sequences are equal, then you can immediately claim, even though, by the way, you are looking at only a particular class of partitions, you can show, if you go to the proof, you see that is enough. This guarantees that your function is differentiable on that interval, and the common value between these two, whatever you get as your number, is the exact number that you are supposed to calculate this. Okay? And let me give you an example, a little bit harder than that one, but you see it's more manageable, or at least it is completely clear what we are supposed to do. So let me just give you an example. Prove that if x equals to, let me increase the level of difficulty a little bit, x squared, prove that this is integrable on 0 and 1, and determine integral from 0 to 1 f of x dx. So by the way, if you see such a simple question in the exam, you just calculate it. It is so simple. Don't get confused. This is just proving integrability from first principles. Yes? Okay, so what should I do? I can use this. So let us just do that. For example, if I want to use this theorem, I need to write the lower sum for a regular generic partition Pn. Okay, so let me just not write anything. So assume that this is my partition, and I want to write LF of Pn. Okay, I ask for your help. Okay, so let us review things a little bit. So I will start writing LF Pn. Okay, don't forget, Pn is just exactly that Pn that I have written up there. So how should I write this? Do you remember the definition? The definition tells you that this is sigma over I from 1 to n, mi, and delta x. Do I need to write delta xi? No, not anymore, because that's a regular partition and the lengths of all intervals are the same. So I don't need to equip them with an index I, because the lengths are all the same. By the way, can you tell me what is delta x here in this problem? Is the total length of my interval, which in this case is 1, divided by n. So that's nothing except 1 over n. Okay, so I take this out. 1 over n is independent of the counter of the sigma, so I can pull it out. Then it becomes sigma mi, I goes from 1 to n. Okay, but if I ask you what is mi, what is mi? Mi, the minimum of f on the ith interval. But what is the ith interval? Do you remember last time? It starts from xi minus 1 and goes to xi. Yes? So to understand this better, let me draw a diagram for you here. Okay, so I exaggerate a little bit here. So assume that here is 1 and here is also 1. So this is the famous parabola. I don't care about this part that much, so let me just draw this one. So that's your parabola, okay? And what I do, I concentrate here on the ith interval. What is ith interval? It goes from xi minus 1 to xi, yes? And then let us look on this interval, what is happening, okay? This is a representative of all these subintervals. Okay, now I am asking you, I am on this interval, this is my function, mi is the minimum value of my function on this interval. What is the minimum value? I can simply show it with my hand, yes? On this interval, the minimum value is this, yes? So the minimum value occurs when x is equal to x sub I minus 1. So this means that if I ask you, what is this length? You can immediately answer me. It is what? It is f of xi minus 1. Agree? So that is f of xi minus 1. Okay, but I know my function. My function is a squaring function. So what happens here? This is nothing except xi minus 1 squared. Yes, because f of x is x squared, so f of xi minus 1 is xi minus 1 squared. Yes? Happy? Yes? Okay. And now I want to talk a little bit about xi's. Do you remember how can I calculate xi? So xi means the ith point. How many sub-intervals I go to reach here? So let me just draw this one for you here. Here is x0, which is 0. The next one is x1. The next one is x2. The next one is x3, and you can continue. If I ask you what is this, that is delta x. That is also delta x, because all of them are now the same, yes? So if I want to find x1, that is 1 delta x. If I want to find x2, that is 2 delta x. x3, that is 3 delta x. So if I ask you what is xi, you would say that this is I delta x. Yes? But I is just I, but delta x I know is 1 over n. So this is I over n. So xi is I over n. Okay, but I need x sub I minus 1. That is also easy. When x sub I is I over n, what is xi sub minus 1? X sub I minus 1 is I minus 1 over n. Agree? And then finally, I have this one. So finally, I realize that I go back again to this calculation. So the lower sum becomes equal to 1 over n sigma I goes from 1 to n mi. But mi is this value. Yes, this is mi. And mi is this expression. And this expression is this 1 to power 2. So let me write and ask you, are you happy with that or not? Yes? Understandable? So what I have done, mi is f of xi minus 1. This is equal to xi minus 1 squared. Xi minus 1 is this guy, so I raise it to power 2. And then, again, this becomes 1 over n sigma. I raise it to power 2, it becomes I minus 1 to power 2, and then n squared. I goes from 1 to n, but again, this n squared can be pulled out because it does not depend to the counter. So this becomes 1 over n to the power of 3 sigma. I goes from 1n I minus 1 squared. And then I have to calculate that sum. I don't want to calculate for you. I want to use my memory to write the formula there, okay? So that is actually simple. So if I ask you what is this, if you expand the sigma, if I put I, 1, it becomes 0 squared. If I put I equals to 2, it becomes 1 squared. If I put 3, it becomes 2 squared. And then I continue, this becomes n minus 1 squared, yes? And this is a very famous sum in mathematics, the sum of squares. Okay, the sum of squares has a formula. So this becomes the formula for this. So let me copy and paste the first part. The formula for this is n minus 1, n and 2n minus 1 divided by 6. You can prove it by mathematical induction. I don't know how many of you have already studied Math 5 in high school, but that's a very simple task to do. So you just use mathematical induction to prove this formula, okay? And then this n and that n are canceled. So what happens is n minus 1, 2n minus 1, divided by 6n squared, yes? And then, so this is my lower sum. But what I need to calculate is the limit of my lower sum when n goes to infinity. So I calculate the limit of lower sum when n goes to infinity. Okay, can you calculate it in your head? This shouldn't be hard for you, yes? What is the answer? N goes to infinity. No, they have the same degree. Because this is n squared, and if you multiply, that's also n squared. So they have of the same power. None of them will dominate over the other one, yes? So what's the answer? Okay, so if you want, I can divide everything by n squared. Do you remember? You have to divide by the highest power. But when I divide the denominator by n squared, it is simply 6. But when I want to divide the numerator by n squared, I take one n and give it to this guy, and then divide it. And the other n I take and give it to this guy, and then divide it. Is that understandable? So I have divided both numerator and the denominator by n squared in that way. And then if I send n to infinity, it is simple. 1 over n is 0. 1 over n is again 0. So it is 1 times 2 divided by 6, which is a third. Yes? So this means that I was able to calculate the limit of the lower sum. But the problem is not finished. I have to calculate the limit of the upper sum. If I am lucky and these two numbers become the same, then I would say that, okay, this is integrable, and the common value is my integral. Okay, so let us just immediately repeat what happens if I want to calculate the upper sum. Okay, now I want your help again. So let us review everything from the scratch. So first you need to write the definition. What is the definition? Again, because that is a regular partition, I don't need to equip this with I. All of them are the same. But and I already know delta x is 1 over n. But that is up to you to tell me what is capital MI this time. What is capital MI? Do you remember the definition? Capital MI is the maximum of f on which interval? Exactly the same interval. Yes? That is MI. And I can show it by hand again. Yes? This is the highest value on that interval. So if I ask you what is this, you will tell me this is nothing except MI. But what is MI? MI is the height of my function when x is xi. So this is just f of xi. Yes? And what is f of x? F of x is x squared. So f of xi is also xi squared. But what is xi? I have it on the board. Xi is this guy. So this becomes I squared over n squared. So I put it back there. So this means that u, f and pn is equal to the sigma I goes from 1 to n. Instead of mi, I write I squared over n squared. Instead of delta x, I put 1 over. Yes? And then this becomes exactly the same. 1 over n3 goes out. Sigma I goes from 1 to n. More or less, I get the same sort of sigma with a little bit of shift. Yes? If I expand that sigma, this becomes n to the power of 3. If I put 1, it becomes 1 squared. If I put 2, it becomes 2 squared. I have to continue until n squared. Essentially, this is the same sum. But it starts from 1 up to n minus 1 squared. This one starts from 1 and goes up to n. So that would be the same formula. The only difference is that I have to change n to n plus 1. If I change n to n plus 1, not here, because that's the same thing. So this becomes 1 over n cubed. I change n to n plus 1 here. Divided by 6. And now what I want to do, I want to calculate the limit of u f of pn when n goes to infinity. So this means that I am interested in calculating this limit. By the way, this n and that n are gone. So what is left in the numerator is this. What is in the denominator is 6n squared. And then n goes to infinity. So what is this limit exactly with the same method? Can you tell me? With the same trick. 1/3. Yes, that's 1/3 again. And then End of story, yes? Because I was lucky and I saw that these two numbers are exactly the same, so I will come to you. So this means that the function is integrable, yes? So I would say that limit of L, f and Pn is equal to the limit of U, f and Pn, yes, is equal to 1/3. This means that f is integrable on 0 and 1, and moreover, what we have, integral from 0 to 1 x squared dx is 1/3. But still, you appreciate Newton's formula, yes? Because it was just a matter of seconds to answer this. Because you just write x to the power of 3 divided by 3, and you put 1 and 0 subtract. But that is how it works. But, yes, Navi? Yeah, I will come to that. That's actually a very important question. Okay, so what I want to now show that, you see that this is, sometimes you might say that, okay, it is just more tedious, but it works. No, I just want to show you that this is not always the case. Because what is the main obstacle in this calculation in front of me to be able to get that answer? And that is a serious problem. So even though from first principles you can calculate something, but Newton's formula is looking into this problem from a different perspective, and it is more powerful, not just it's simpler in calculation. So can you tell me, if you see here, what is the hard part in this calculation? Forget about how lengthy is that, but there is one part which is the hard part in this calculation. I mean that if you want to say which one is harder, which one do you point at? Yes? This one? No, I wouldn't say this is hard, because here in this case it was extremely simple, I agree, but this is not an obstacle in front of us because we can use derivative to find maximum and minimum. Yes, here it was so simple that I just by looking at it, I was able to find the maximum and minimum by just looking at it. Yes, but that is not the main problem in front of us. Yes, it becomes more tedious, I agree with you, but we already know how to calculate the maximum and minimum value for a continuous function on an interval. So we have an algorithm for that. Yes, so that is, I would say that is not the hard part. If the function is not so simple, then of course I have to work more. But we can do that. But there is something really practically impossible if I change my function. For example, can I ask you, instead of this function, let me ask you a question in this different way. If I change my function to this function, square root of x, then let us review what will happen. Yes? So what will happen, do you think? You see, this part will not be different because this function is still increasing. Yes? So this means that the minimum value will be here still, the maximum value will be here, but of course with a different value. So in that case, the value becomes this one for minimum and this one for maximum. Yes? But it will go up to here, and this will reveal itself here. So it becomes a square root of I minus 1 instead of a square of it. Yes? And then if I expand that sigma, the sigma becomes a square root of 0, square root of 1, a square root of 2, up to a square root of n minus 1. Yes? And then divided by, for example, in this case, is it n cubed? No. That is also a little bit tricky because this becomes a square root, a square root of n, something like this. Okay, don't worry about the details. You can check it later. But the point is that here, I had a formula for this sum. I was able to write it in a closed form. A closed form means a formula without these three dots. I was able to take this and write a formula for it. But here, I don't have any formula. Yes, I do not have any formula so that I can give you this sum as a closed formula. I cannot just simply do that. So this means that I don't know even how to calculate the limit at the end. Because here, I was able to get rid of this sum and write it in a more compact form. And then instead of taking the limit of this, I took the limit of this one, which was manageable. But if I get here, everything will be here, but I will be stuck here. And there is no way for me to solve it. So I just want to tell you that even though this problem is also extremely simple, but you cannot use these principles to calculate that limit. Yes, so that would be a dead end for this method. So, but if I give you this integral, it should be also a matter of seconds for you to solve using Newton's formula. So it means that not only it is looking at the problem in a different way, but it's actually expanding your tools, extending your tools so that you can solve harder problems that you couldn't solve using the first principles. It's exactly like derivatives. Once for all, we proved the chain rule, and then we started using the chain rule. Assume that I write a very horrible function in front of you, and I ask you to calculate that using the first principles by taking the limit of whatever. It's not possible. So it means that the chain rule is also a very vital theorem, a very important theorem in the field of derivatives. Yes? Okay, so let me give you a little bit of a break, and then we come back to this and continue with this lesson again, because there are some problems here that I want you to understand, especially the calculating these limits. So now you understand why calculating limits like that is related to this problem. Because Newton's told me how to calculate this integral. On the other hand, I know the integral is related to this limit. So I am actually abusing the logic here. So in principle, I have to calculate this to answer the integral. But because Newton's formula gives me a better way to calculate this integral, I calculate that integral, and then using that integral, I calculate the limit. Yes, so that is the logic. I will come back to this in the next part of the lesson. Okay, thank you. So let me just, this time, hopefully it is recorded. Yeah, it seems that, and start, I think. Thank you very much. Okay, now let us go back to what you asked, Navid, about this. So we had this before. Do you remember? Let us review a little bit. What was the relation between differentiability and continuity, just for practice and refreshing your memory? There was a connection between differentiability and actually, can you see the voice is also being recorded? Yeah, it's going up and down?
Yeah.
Okay, good, thank you. So what was the relation between continuity and differentiability? So let me just review it for fun. It's not related to this problem, but what was that? Differentiability, do you remember? Let me write it for short, implies continuity, yes? So it means that if a function is differentiable at a point, it is definitely continuous at that point. So, and I told you that every implication in mathematics is equivalent to contrapositive, actually, a statement. Means that you swap these two and negate them simultaneously. Yes, this is not Q, not P. So this is always the case. So when you prove that an implication is true, it means that it's contrapositive. This is called the contrapositive implication of this implication. That's also true because they are equivalent. Okay, so this means that immediately I can conclude that discontinuity implies non-differentiability. Yes, that is also true. So this is true, this is true. But if you mistakenly write continuity implies differentiability, that is false, yes? Okay, so I don't know how to write it. Let me just cross it over, it's better. Can you give me an example that this does not work? Absolute value exactly at the origin. It's a sharp point. So the absolute value is continuous. I can draw the graph with one pen stroke, but because that sharp point it is not differentiable, but it is continuous. Yes, we want to find another relation between integrability and continuity without proof, because the proof is higher than the level of discourse. So the theorem is this: if f is continuous on A and B, then f is integrable on A and B. So this time continuity implies integrability. Yes, so continuity, I don't know if it's a good way of writing it, but you understand what I mean. Continuity implies integrability. Okay? And then I told you that because of this rule, non-integrability implies discontinuity. Yes? But the proof is not easy as the previous ones, but you have to know it, okay? But then, of course, don't fall into this trap that integrability implies continuity. So if you write integrability implies continuity, that is wrong. Continuity, is that right? Yes, anyway. So continuity. This is false. Okay? And then if I want to give you an example, it is doable, I think, at the level of your knowledge, but it takes time. If you want like these kinds of problems, you can think about it. So I would say that let f of x be equals, for example, to this function. I take it 0 if x is between 0 and 1/2, and I take it to be 1 if x is from 1/2 to 1, is integrable on 0 to 1, but not continuous. Yes? So using the definition, of course, here you can also use Newton's theorem, but of course, Newton's theorem can be calculated for this one piecewise. So for example, if you want to calculate integral from 0 to 1, f of x dx, you cannot use the Newton's theorem for this because that's also discontinuous, but you know that you can break this integral from 0 to 1/2 and then plus 1/2 to 1, yes? On 0, 1/2, I use this part, which is continuous. On 1/2 to 1, I use this part, which is also continuous, yes? So I can break my integral into two parts, and then I can calculate this. So it is clear that this is integrable, but in principle, if you want to solve it, you have to solve it from the first principles. But this is obviously not continuous. Why? Because if I draw the graph of this function is nothing. It is from 0 to 1/2, it is 0. Yes? This is 1/2. And then it is 1 when it is from 1/2 to 1. So here is 1, and then this becomes this. Something like that. So it is clear that this function is not continuous. But you can convince yourself that this function is integrable. So integrability does not imply continuity. Okay? Okay, so that is something that I want you to know. And the last part of the lesson is talking about Riemann sums. Yes? So what do I mean by a Riemann sum? First of all, let me define you what do I mean. Adams used a word called tag. So let me tell you what tag is. It's a very simple idea. It's a good thing. I haven't heard about this before reading this text, but that's a good thing. So
what I have is this. Assume that you have a function. No, let me just forget about the function. You have an interval which is from A to B, and then you have a partition for A and B, not necessarily regular, every partition that you like. So it starts from X node, which is by definition A, and then X1, X2, up to Xn minus 1, and the last one is B. So this is your partition, yes? Okay, if an n-tuple C, C1, C2, up to Cn is called a tag for this partition for P if Ci belongs to the ith interval. That's a tag. It's a good name because I want to refer to this. So it means that what is the meaning of this? So do you remember I have A here, which is X node, and then I have somewhere X1, a little bit later I have X2, not necessarily, I have, for example, X3, and I have X4 here, and let us take it 5 points, okay? X5, which is, for example, B. Yes? This is assuming that this is your partition, that you have 5 subintervals. Okay, the first subinterval is from here to here. The second subinterval is from here, including. So these points are both for the left subinterval and for the right subinterval, remember. So, and second interval is from here to here, third, fourth, and then fifth. So if you choose any number here, for example, let me choose this number here, C1. I don't know, I can choose number C2 here. I can choose number C3 to be X3 itself. I can choose, I don't know, C4 here. So 1, 2, 3, 4, 5. It should be 5. What I'm missing? Okay, I missed this one. So this is C5, and this is, for example, C4. Okay, then these numbers, if I arrange them in a tuple, so here it's a 5 tuple, that is called a tag for this partition. Okay, so when you have a partition, you have some points, you have some subintervals. If you choose any point from that interval, from each interval, if you choose one number from each subinterval and arrange them in an ordered way here, that tuple that you get is called a tag for your partition. Yes? So to test your understanding, how many tags we can assign to any partition? How many? Infinitely, for any partition. I give you one partition and I'm asking you how many tags you can assume for that particular partition. I am asking you in how many ways you can choose these numbers. In how many ways? Infinitely many ways. So for each partition, you have infinitely many tags that you can associate with. Yes? Is that clear? Okay. Now, this is important for the notion of the Riemann sum. For the Riemann sum, what I mean is this. So assume that now if I give you f, which is a bounded function on a closed interval a and b, yes, and then I define a sum in this form. I would say that let P be a partition for this interval, x node, x1, up to xn. The first one is always the initial point, the last one is always the final point. So you have a function which is bounded on this closed interval, and then you have a partition for that closed interval, not necessarily regular, any arbitrary partition. And then you define, and then you choose a tag for that. Okay, so for example, C1 up to Cn is a tag for P. Yes? And then you set up this sum. You write sigma of f of ci times delta xi, and I goes from 1 to n. This is called the Riemann sum for your function corresponding to this partition and this tag. Yes? So that's the meaning of the Riemann sum. So is that clear? So can I say, for example, let me test your understanding again. So first of all, tell me, is that understandable? So I give you a function, an interval, and I give you a partition for that interval. You go and find a tag for that partition. You have infinitely many choices. You have one of them. Let me say that this is C. And then what you do, you pick up the first number, put it into your function. It becomes f of C1. And then you multiply it by the length of the first partition. And then you go to the next tag, C2, pick it up, put it into the function, it becomes f of C2, and you multiply it by the length of the second partition. And you continue until you finish everything, and then you add these numbers up. So this becomes a sum, which is called the Riemann sum of your function corresponding to this partition P and tag C. For example, I can keep f fixed. I can change P. In general, the sum will be changed if I change these numbers. Yes? I can keep F and P fixed. I can change only the tags. Again, the Riemann sum will change. Is that understandable? So this value that I get at the end is sensitive to both P, a choice of P, and a choice of tags. Yes? Okay, so that's the Riemann sum. For example, can you tell me, can I say a lower sum is also a Riemann sum? Yes. Why is that? Of course, for the cases that the function is continuous. Do you know why? Because if the function is only bounded, it is possible that the maximum or minimum values are not attained. So we call them the least upper bound and the greatest lower bound, yes? So assuming that the function is continuous, yes, you are right. A lower sum is also a Riemann sum. Can you tell me what are those tags in that case? When I write a lower sum, assuming that the function is continuous for the time being, okay? By the way, it might be better if no, here it doesn't matter actually, so it can also be bounded. But let us consider, from now on, consider that the function is continuous. So if I ask you what is the lower sum, what do? You write sigma mi delta xi. So this delta xi part is similar, but instead of f of ci, I have mi. But mi is the minimum value on the ith interval. And if the function is continuous, that minimum is attained for some number. So in that case, C1 is the number so that that minimum value is attained. So we can say that in this case, the lower sum for continuous functions is also a particular form of the general Riemann sums. Okay? And the same thing for the upper sums. Okay, but something, I want to write something. If I give you this P and this, so let me tell you something. So for writing the lower sum and the upper sum, I only need the function and the partition. I don't need the tags, okay? Because you see there is no track of tags here. So I give you F and I give you partition. You can set up the lower sum for me. You can also set up an upper sum for me, yes? But now I give you also a tag. Then after that, you can also set up a Riemann sum for me. Now my question is that how the value of this Riemann sum is related to those lower sums and upper sums. Is the question clear? I give you a function and a partition. You immediately set up, you make a number for me, is called lower sum. You know how to calculate it, and you find a number for me is called upper sum. And now I give you extra piece of information. I also give you a tag. And then you set up a Riemann sum for me using the same function, the same partition, but this tag that I just gave to you. It becomes a number. My question, how this number is related to those numbers? Is there any nice relation between them? Yes, exactly. It's between them. It is squeezed between them, yes? So this is definitely true. This is the case. This is always the case. For which tag? For every tag. So I would say that this is always possible for every tag. Yes? So this is we know. Why is that? Because I told you that f of ci is always, whatever ci is, it doesn't matter. It is always less than or equal to the maximum, is always greater than or equal to the minimum. So term by term, these terms are sandwiched between those terms. So it means that the sum is also sandwiched between those sums, yes? Okay, but now the question is, if the function is integrable, okay, if f is integrable on, if f is integrable on the interval a and b, so what can I say? I want to talk about the limit of the Riemann sum, okay, when I send the number of partitions to infinity. So the notation that Adams uses is the n, the number of subintervals of this partition P. I want to send it to infinity. Okay, assuming that f is integrable. Yes? What can you say about this limit then? If that is integrable, yes? Yeah, it should be the regular integral, yes? If that is integrable, because this, do you remember, these two will approach to the value of the integral, and this is sandwiched between them. So this actually goes to the integral from where to where? A to b f of x dx. Yes? But this is extremely important. First, if you want to use such a scenario, you have to prove first that the function involved is integrable in the first place, and then you can use this rule. But of course, this is a little bit, to be honest, wrong. Can you tell me why this might be wrong? Because if I increase the number of subintervals, it is not enough. Why? Because, for example, I don't know how to say. For example, here is A, here is B. Assume that I divide it into, I don't know, 1, 2, 3, 4 parts. Okay? Don't think that this is the case. If I increase the number of subintervals, is it guaranteed that the lengths of all of them are getting closer to 0 or not? In a regular partition, yes, because I am chopping the interval into equal pieces. If I divide it into 3 pieces, the length would be a third of the total length. If I chop it into 4 pieces, the lengths of each one of them becomes smaller, yes? But not necessarily for a random partition, yes? If I have a random partition, and I just tell you, increase the number of subintervals, is it necessarily guaranteed that the lengths of all subintervals are also shrinking to 0? Yes or no? Do you understand the question? No, the question is that I want to increase the number of points. The first intuition might be that, yes, if you increase the number of points, of course, these are getting smaller and smaller. Yes, that's correct. And if I increase it to 100 points, then everything probably becomes smaller and smaller. But I am saying not necessarily. If it is a regular one, yes, you are right. Because in a regular one, if I divide it into 2 pieces, each piece has 1/2 of the total length. If I divide it to 3 pieces, each piece will be a third of the total length. So everything becomes smaller. But in principle, I can keep one of these two, I can keep these 2 points the same. For example, x1 and x2 the same. And I start increasing numbers here, yes, and there. Okay, so it means that it doesn't matter how many subintervals I get, I decided to keep this one fixed. So this will be make a problem for me. So I want to prevent such a scenario. So I not only say that NP should go to infinity, I also say that the gap, which is the maximum length, should go to 0. And that gap, in Adams, it is written the norm. In some books, they say gap of the partition. So if I ask you what is the gap of a partition, it is the longest subinterval, the length of the longest subinterval. So norm of P is the maximum of the length of the subinterval. Yes? By sending this to 0, I am preventing this scenario. Okay? But remember, for the case that you are facing regular partitions, you don't need to add this by hand. Automatically, it is fulfilled. Because for the regular partition, this is this case, yes? The lengthless of all subintervals is this one. And when I increase n, automatically the lengthless of all subintervals are getting close to 0. So I don't need to add this by hand there. Okay? So remember, if f is integrable, and then you have a Riemann sum, it doesn't matter what is that Riemann sum. What matters is that the gap also starts going to 0 by increasing the number of subintervals. If you have such a Riemann sum in your hand available, if you take the limit of that Riemann sum, it becomes exactly equal to the integral of your function. Okay? And that is actually the last part of the lesson that I want to start teaching you. Okay, that's important because I have seen some questions in the exam were actually hard. Okay, let us understand this problem with a very, very simple setup. Okay, now let me tell you something. The reason that I highlighted this, I have written it as a theorem, but it is a problem in Adams because most of the exam problems are being solved with this particular Riemann sum. But by no means it is the only way that you can solve the problem. But when I checked all the many examples in the exam, actually I didn't see any deviation. Yes, in one case, actually the examiner tried to do it in a different way, but still that problem, because when I saw the solution, he solved it in a different way, but I also solved it using this formula. So in principle, I didn't see any example other than that in the exams. So this is why I highlighted this for you, but let us understand the content and then we can actually write some things, some other formulas for yourself. It is not an easy problem always. Designing that question is easy because first you write a function and then you go you reverse engineer it and find that limit and then give it to poor students to solve it, yes? Because they have to reverse engineer the other way around, okay? Okay, so that's the way that mathematicians become happy, yes? Yes. Anyway, so let us just try to see how it goes. And I have, by the way, because I didn't mean to teach you integrability, I changed my mind. I have written here continuous, okay? Continuous automatically guarantees integrability, but you can cross it over and say integrable, yes? But most of the time, continuity is the tool in your hand. You see continuity, you conclude integrability, and then you can use the theorem, okay? But let us try to understand that part. So first, let me give you, let f be integrable. So I am deviating a little bit from there. Be integrable on 0 and 1. Okay? I want to show that the limit of 1 over n sigma f of k over n, k goes from 1 to n, and when n goes to infinity, is equal to integral from 0 to 1 f of x dx. So that's my goal to prove, yes? So according to what we did on the board here, so I have to I have to convince you that the left-hand side is a limit for a particular Riemann sum. Yes? If I can convince you, then I can use that theorem and prove this. Actually, the proof is there. Okay? So what is this? Can you see that this is a Riemann sum? So how should I know that? For example, this 1 over n is some indication about the length of each subinterval. Yes? So in this case, apparently it seems that this is a regular partition. Okay? So delta x is 1 minus 0 divided by n, which is 1 over n. Okay, so this guy probably can play the role of my delta x. Okay, but now let me partition interval from 0 to 1. Okay, and then let us concentrate on this ith interval. Okay, and I don't care about what is my function. I don't care about it. Okay, so what I do, I calculate these. So can you tell me what is xi? Do you remember? Xi is the first number a plus I times the length of this interval. But in this case, a is 0, I is just I, and delta x is 1 over n. So it is I over n. And for the same reason, x sub I minus 1 is I minus 1n. So if I ask you what is the ith interval, so what is the ith interval? It is xi minus 1 and xi, which is I minus 1n and in. Okay? So by the way, if you, I should have used letter I consistently. So if you don't mind, I change this letter K to A to I so that you are not confused. It doesn't matter. Okay. Yes? No, A is the first number. Yes? And B is the last number. So A is the initial point of my interval, B is the final point. Yes? Pardon? No, I usually calculate for xi, and then for xi minus 1, I replace I with I minus 1. This is easier. Yes? No, this is the formula. I have it in mind. Xi, the ith point, is the first point plus I times these lengths. Yes? Okay, do you agree that this is the ith interval? Okay, now this is the time that you have to fine-tune your tags according to the problem in hand, because you have infinitely many choices. I told you, for tags, you have infinitely many choices. But look at the function. This is f of I over n. Is I over n somewhere here in this ith interval? The answer is yes. It is the final point. Can final point be chosen as a tag? Yes. So this means that for this particular problem, the designer of the question has chosen the last point of each subinterval to be the tag of that subinterval. Yes. Now I ask you, give the role of tag Ci to this guy and write your Riemann sum. So what was your Riemann sum? Riemann sum of f, p, and c, by definition, is sigma f of Ci delta x. I goes from 1 to n. Do you agree? That is the definition of my Riemann sum. But now here I decided to choose tags to be the final points. So instead of Ci, you write this. Sigma f, instead of Ci, you write I over n. Instead of delta x, you put 1 over n. And I goes from 1 to n. Agree? But this 1 over n goes out. Sigma f of I over n, I goes from 1 to n. So I realized that the Riemann sum, this particular Riemann sum, takes the form that I need. And now I take the limit of R, F, P, and C. In this case, I just tell you that NP should go to infinity. By the way, NP is just n in this problem, yes? And do I need to write the gap should go to 0? No, automatically the gap goes to 0. Yes, I don't need to emphasize on that. So this becomes the limit of, let me write n. Okay, don't need to write s to it. So n goes to infinity, n sigma f of I over n. I goes from 1 to n. So I hope that I could convince you this is the correct formula. But on the other hand, we know that f is integrable. So if f is integrable, I already know the limit of the left-hand side, which is integral from 0 to 1 f of x dx. So this means that this limit is equal to this integral. Yes, understandable? Yes? Yes, yes. But what I have done, I changed it a little bit because I have used I all the way around so far. So I changed the letter K to I everywhere. No. It goes from 0 to... it is wrong. Yes, you are right. Please correct it for me. Thank you. Thank you very much. This goes from 1. Yeah, thank you very much. No, this is the correct one. Yes, you have to correct that. Thanks. Yes, is that clear? So this is the most ubiquitous formula that you use in exam when it comes to these kinds of problems. Yes, do you have questions?
Yes, I think I didn't get to hear the last part about explaining why it's actually equal to the limit of the integral between 1 and 0 of the original function.
No, I proved this for you that this fun is equal to that one. So this means that when I take the limit of this, which becomes this, is equal to the limit of this. But this one is on the board. The limit of a Riemann sum, if the function is integrable, is equal to the integral. Yes? From a to b. But in this problem, a is 0, b is 1. So this becomes from 0 to 1. Yes? Is that clear? So this is always true. And I am combining this problem and this argument to use it in a way that is useful here. Yes? So let me solve some simple questions for you. For example, you see this sum. The limit of 1 over n, what is that? A cosine of 1 over n plus cosine of 2 over n plus up to cosine of n over n. N goes to infinity. Okay? Okay, let me ask you one question. Because do you buy this argument from me? When n goes to infinity, what happens actually? 1 over n is 0. So cosine of 0 is 1. 2 over n is also 0. So cosine of 0 is 1. And if you continue, all of these are probably 0 or no. Might be that is not correct. Yeah, this does not work here. Okay, so I probably need to go to the next example to ask you the same question. It does not work here. Okay, but you want to find this limit. I don't know, can you feel the connection between this limit and this limit? Yes, because you see 1 over n here, it's also 1 over n. I would recommend you to write this in a sigma form, if it is not already written in sigma form. So what you write the limit, 1 over n is 1 over n, and then you write a sigma, and can you write this in the sigma form? Okay, how should I write it in a sigma form? It is cosine of 1 over n, then it becomes 2 over n, then it becomes 3 over n. So I can write it as I over n, and I goes from 1 to n. Agree? Now look here what is happening. Compare this limit with this limit. It's very similar, yes? 1 over n, 1 over n. But instead of having f of I over n, I have cosine of I over n. So can you guess what is playing the role of your function f here? Cosine of x. Yes. So by comparing these two, you immediately realize that if I take, so that is the reverse engineering part. Yes. You need to guess which function is responsible for this Riemann sum. Yes. And this is not hard by just comparing them. So f of x is cosine x. If I tell you f of x is cosine x, I hope that you agree with me. This is nothing except limit of 1 over n sigma f of I over n goes to infinity. So you introduce this function, okay? And by introducing this function, do you agree that I can write this in this form? Yes? And now you need to use this formula. But before using the formula, you have to motivate why you can use the formula. So you have to motivate that the function is integrable. And the main tool in your hand is continuity. Yes? So is this function continuous on 0 and 1? The answer is yes. So you need to write them down. The function cosine that you defined is continuous on this 0 and 1. Because it is continuous, it is also integrable. And because it is integrable, this limit becomes the integral from 0 to 1 cosine x dx. So instead of calculating this limit, you calculate this integral. But that's extremely simple because you can now use Newton's formula to calculate it. Yes, it is continuous, so you can work with it. So the primitive function for cosine is sine, so you have to calculate it between 0 and 1. So this becomes sine of 1 minus sine of 0. Sine of 0 is 0. Sine of 1 is just sine 1. And remember, 1 is in radians. So might be you couldn't guess this value for this limit, but the limit of this is sine of 1 radian. Yes, is that clear? Let me immediately solve you the next problem. So the limit of 1 over n plus 1 and 1 over n plus 2, and then you continue 1 over, I have written 2n. Do you understand why it should be suddenly 2n at the end? Do you see that if pattern continues like that, the last term becomes 2n? Why? Why? Because it becomes n plus 1 first. The next one is n plus 2. I continue this process until I reach to n plus n, which is 2n. Okay? Is that understandable? So don't think that how strange this pattern is. No, it's not strange. N plus 1, n plus 2, the next one, n plus 3. I continue this process so that I reach to n plus n. But of course, n plus n has a better name, so I wrote it 2n. Okay, so you want to calculate this limit. Okay, do you remember I asked you a question that didn't work here? This will work here. If I ask you what is the limit of the first one, what's your answer? 0. What's the limit of the second one? And what's the limit of the last one if you continue part by part? So is the limit 0? Because the limit of each part is 0. So is the limit of the sum 0 as well? That's the point. If this is so simple, I wouldn't ask you, yes? So there is a point in it. The answer is no. But can you tell me why? Thank you. You just said why, yes? Okay. Why? Because the number of terms goes to infinity. So each one of these, by the way, the limit is 0. So it means each one of them is an infinitesimal number. But how many terms I have? I have n terms. N is going to infinity. So each term, you are right, is infinitesimal. In the limit, it is 0. But how many zeros I have? Infinitely many. So it is indeterminate. It is infinitely many zeros. It means infinite times 0. So the answer is not that simple 0. Yes? Okay, but now we want to calculate it. I have 2 minutes. Let me calculate it quickly, okay? If I want to do this, I told you that main theorem is this one. But there is something that is missing. First of all, I tell you, write it in the form of a sigma. Can you write it down? So the limit n infinity, how can I write it as sigma? Sigma, I goes from 1 to n. Do you agree that I can write it like this? Yes? So it becomes 1 over n plus I. Yes? I goes from 1 to n. Do you agree? Yes, that is the sigma form. But start comparing what you need to what you have. What you need is 1 over n here, which you don't have here. So we have to somehow make this appear. But that is easy. How can I do that? I just factor. Yes? So this becomes sigma, I goes 1 to n. I factor 1 over n out. It becomes 1 plus I over n. Do you agree? So what was the motivation? Because if you understand that this problem is supposed to be solved using this trick, then you need this 1 over n or whatever like that there. So this motivated me to make it transparent here so that I can see 1 over n. What I do, I factor 1 over 2. Do you understand the algebra? Yes, if you multiply this back, I get the same thing. But this 1 over n goes out because this n does not depend to the counter. So n goes to infinity. So this becomes the limit 1 over n sigma 1 plus I over n. I goes from 1 to n. But now, can you reverse engineer your function now? You want a function, you have to guess a function whose f of I over n is that function that appears. You want to give the role of f of I n to this one. You don't know what function is, but you need to guess a function f so that f of I over n becomes this combination. Extremely simple to guess, yes? So what is that function? Can you tell me? Okay? F of x is which function? Thank you. 1 over 1 plus x. Yes? Why is that? Because if I ask you what is f of I over n, you replace x with I over n and you get that function. Yes? That expression. Understandable? So that is the hard part. You need to guess the function. Okay? Sometimes it might be hard if you see some problems. Okay? So here, what I do, and then I want to write it from 0 to 1. My function, which is this function, dx. But before doing that, I have to motivate the examiner that what? This function is integrable. Why is it integrable? This function is continuous on the interval 0 to 1. So so you have to write these things down, okay? So this function is continuous, so it is integrable, so everything is valid, and hopefully you know what is the value. What is the integral here? ln of absolute value of 1 plus x. X goes from 0 to 1. You put 1 here, it becomes ln of 2. You put 0 here, ln of 1 is 0. So the answer is surprisingly ln of 2, yes? You might not able to guess that the limit is ln of 2. So the limit is ln of 2. Okay? But of course, the problems could be harder than that. So this one is probably the hardest one I saw in the exam. Exam 2020, this one is somehow related to this, but I will solve this one for you because that is also somehow improper integrals. Okay, so these problems that are left, if we get some time at the very end lesson, or if you want, we can extend that lesson a little bit so that we can cover these questions and whatever you need to ask me, okay? But at least, hopefully you understand now how these things work. Okay, thank you very much. I hope that this time it is recording, is it? Yeah, thank you.